We're going to be looking at the derivatives of inverse functions today, but I wanted us to review really quick what we knew about a function and its inverse. So actually the class has kind of spent some time and brainstormed a little bit and thought about this, and we've discussed it, and I wrote this out, but I want to, because I didn't record, go over it a little bit. And so first thing that was discussed is that we know that the input and output of one is reversed. It's the output input of the other. Their x and y are swapped. Input and output are swapped for the function and its inverse function. And so for instance, if we had this point xy here, then we know the point on the inverse function, swapping our x and y values would be y comma x. So another way to say that is the domain and range. The input is our domain, the range is our output of one function are going to be the opposite. So for our inverse function, the range of our original function is now our domain. And the domain of our original function is now the range of the other function. In order for two functions to be inverses, a couple of things need to hold. So in order for a function f of x and f inverse of x to be inverses, we must be able to, when we take the composition of the function, which written in this notation, same as this, you have to get back x. We talked about composition of functions not always being commutative. If you take one function's the inner, one function's the outer, and you swap them, you don't always get the same thing. So order matters. But when you're looking at a composition of inverse functions, you'll always get back, doesn't matter the order, the back x. They undo each other. In order for a function to have an inverse, it has to be a special function. It has to be a one-to-one function. So for every x value, corresponds to only one y value as a function, but every y value that we have is only corresponded to one input of one x value. And we talked about really quickly that there are functions that are not one-to-one, but if we narrow down our domain of that function, we can make it one-to-one. For instance, if we had, again, a parabola, this is a function. I could do, if this passes my vertical line test, and for every x value corresponds to only one y value. But here's a case where it's not a one-to-one function, because here's a case where here's one x value that gives me the same y value as this x value. It doesn't pass that horizontal line test. But if we narrowed our domain down, so I could either say x is strictly less than or equal to 0, or x is strictly greater than 0, or greater than or equal to 0, just narrowing it down somehow so that it becomes a one-to-one function. And so if I decide, I can just erase half of this parabola and say, okay, well, f of x is equal to x squared, but we're going to choose x to be strictly greater than or equal to 0. I've now made it a one-to-one function. Okay, so that was a quick review of algebra and inverse functions. And we're doing that because we're going to be looking at the derivative of inverse functions. And so let's derive this formula. We've been doing a lot of that, driving the derivative rules. And we're going to start by looking at the following. We want to find the derivative of f inverse of x. And so recall f inverse of x, the inverse function, we denote it. It looks like a -1 exponent, but that is not the same thing as treating it as a negative exponent. So let's start with what we know. We know that if we have f inverse of f of x, we know that this is the same thing, because they're inverses of one another, x. So now let's take the derivative of both sides. So differentiate both sides of the equation. And so if I take the derivative of that left-hand side, I'm going to have to use the chain rule. So I'm going to look at g dx. I'm just going to write it on the left-hand side of this inverse function, f inverse of x, of f of x, is equal to the derivative, we might as well just write it, d dx of the other side, which is x. So using the chain rule, we know our outer function is this f inverse. So we're going to look at f inverse, the derivative of that, of the inner function. Well, our inner function, right, is f of x. Chain rule, we had to take the derivative, right, times the derivative of the inner. So times the derivative of the inner f prime of x. And this is equal to, well, the derivative of x is just 1. So our goal right now, again, is to find the derivative of f inverse of x. Well, let's first divide both sides by the derivative of f of x. So I'm going to divide both sides by f prime of x. And I have f inverse, the derivative of that, of f of x. Is equal to 1 over f prime of x. I want to manipulate this. And a lot of times, right, and you've seen in this class and a lot of math classes, we're trying to manipulate things to look like we want it to look like. We're multiplying by some fancy one. Yeah, you know what I mean. So we're going to manipulate this. We want this actually f of x piece right here. We want that to be x because we want to know what is the derivative of f inverse of x. And so let's manipulate that. Well, let's choose x. We can choose x to be something. Let x. Well, thinking about what can I plug in for x here? And it could be some function. What can I plug in for here for x that would undo this piece and just give me back x? Well, isn't that part of what we were talking about here? A function and its inverse function would give us back x. And so if we let x equal the inverse function of f of x, and we go back in here and plug it in, we would have the inverse, the derivative of the inverse of f, but now we're replacing x with f inverse of x is equal to 1 over the derivative of f of x f inverse of x. So the whole point of that, right, was so that we could rewrite this piece as x. And by definition, in order for them to be inverse functions, that has to come back to be x. We can do this too because we know that our function, if it has a derivative and it's 1-to-1, it's going to be continuous. And the inverse function, the input-output, it's going to be flopped, but it's also going to be continuous. And so this right here, f inverse, the derivative of, this is now x, is equal to, and now we just found the formula, 1 over the derivative of our original function, plugging in the inverse function of x. So this textbook brings in how we take the derivative of the natural log of x a little differently than how I showed you yesterday. Yesterday, we used the formal definition of derivative to derive the formula for the natural log of x, the derivative of natural log of x. This book brings in this fact of inverse functions and the derivative of inverse functions, and using the fact that we know what the derivative of e to the x is, which is the inverse of natural log of x, to show what the derivative of a natural log of x is. Earlier today, teaching my business calculus, social science, life science calculus course, I showed even a different way of looking at the derivative of the natural log of x. So that's 3 different ways that I've found within the last week of how to find this derivative of natural log of x, which I thought is kind of interesting. Let me pause for a second and then we'll see if you have any questions, and then let's use this fact right here to derive the derivative of natural log of x, which we found yesterday to be 1 over x. Okay, so we're going to look at the derivative of the natural log of x. Again, we derived that yesterday by using the difference quotient and the limit as h goes to 0. This today we're going to prove by using what we just derived, the derivative of the inverse function. So find the derivative of f of x equals ln of x using the derivative of the inverse. So we need to remember what the derivative, or not the derivative, the inverse function is of f of x. And so the inverse of f of x is e raised to the x power. So we want to find part of this in here is finding the derivative of, let's just see, of the inverse function. Now I'm like, pause. Okay, so we want to find the derivative of f of x equals the natural log of x, and we know f inverse of x is equal to e to the x. Well, let's look at this. So if we want the derivative, we're going to let's call g of x equal to e of x. And let's take the derivative of this g of x. Well, we know the derivative of g of x is equal to e to the x. The inverse, though, of this g of x is the natural log of x. So if we want to take the derivative of our inverse function, so the derivative of this inverse function is equal to 1 over the derivative of our original function, which we called e of x. And that derivative of that e of x was e to the x of, so this piece right here, instead of writing x there, we have to write our inverse function. Well, our inverse function, right, was natural log of x. And so remember rules of logs. E raised to the natural log of x is just x. or a, some base a greater than 0, raised to log base a of x is just x. And so here we say that then the derivative of our inverse function, which is natural log of x, that derivative is equal to 1 over x, which we saw yesterday. So f of x equals natural log of x. We saw that the derivative of that is equal to 1 over x. So it's just another way of proving what we had done yesterday. I personally liked what we did yesterday a lot better. And I even think I like what I did this morning even better than that. But I don't know if you really want to see another proof of the same, driving the same thing. So let's jump in. And I think what the most fun part is actually doing examples and not proving as much. So let's jump into some examples finding the derivative of an inverse function and using that rule that we just derived. Okay, so pulling an example from the book, we're looking at finding the inverse function, graphing both the function f of x and its inverse, and evaluating the derivative of f with respect to x at some value x equals a. In our case, a is -1. And our function f of x is 2x plus 3. And we're going to find the derivative of the inverse function at x equals f of a. So the y value when x was a, and show that these points, the derivative of the inverse function of with respect to x is 1 over the derivative of our function dx. Okay, so let's break it down. So the reason why we would want to do this is sometimes it would be hard to find the inverse function. This is not very hard to find the inverse function, right? So to find inverse functions, I normally change, if I have a function notation, I change this in terms of y equals 2x plus 3, and then I would swap my x and my y values and I would solve for y. So swapping x and y, I now have x is equal to 2 times y plus 3. So get y by itself, I would get rid of any terms that didn't have y. I would subtract 3 on both sides, and I get 2y equals x minus 3. Divide both sides by 2. I get that y is equal to, and I'm going to break this down as 1/2 x minus 3/2. Just because that is in the form of y equals mx plus b, I know what my slope is and my y-intercept is in this form. And this, what we just found, is our inverse function, f inverse of x. And we could show that by taking the composition. Either way, we would get back x. So we found f inverse of x, and now wants us to graph both of these. These are both lines. The graphs of a function and an inverse functions are reflections, if you don't remember, are reflections across the line y equals x. So let's graph y equals 2x plus 3. I notice my slope is 2, or I can think of it as 2 over 1, and my y-intercept is 3. So I have a point at 0, 3. And if I use my slope to find other points, I would go down. If I go down 2, I'd have to go over 1 to the left. Negative and negative makes a positive. If I go down another 2, I would go over 1 to the left. If I went up 2, I'd go over 1 to the right. Okay, so graphing that. Oops. We have this line. So this is our f of x function. And now we want to graph f inverse of x. Okay, so this time my y-intercept is -3/2. And that's -1.5, and my slope is 1 over 2. or 1/2. So I'm going to put a point at -3/2, which is again -1.5. And if I rise 1, I'm going to run over 2. Or if I fall 1, I would run over 2. So if I graph this, it's something like looks like this. Oops. And this is my F inverse of X. And like I said, if you notice this should be a reciprocal or reflection across this line, y equals x. So if you folded that paper along that dotted line, it would be laying on top of each other. Okay, so now we want to evaluate the derivative of f of x at x equals a. We want to look at the derivative of f of x at x equals -1. Okay, so the derivative of that's not bad, right? F prime of x, so let's find the derivative first. That's just 2. So there's no x there, and when I evaluate that at -1, well, there's no place to plug in that -1, so this is still just 2. Now we want to evaluate, let's first find the derivative of our inverse function. So if I go down here and I take the derivative of my inverse function, so df inverse of dx, well, taking the derivative of this, well, derivative of 1/2 x is just 1/2. Derivative of constant is 0. And if I evaluate this at my y value, so recall f of -1, well, let's look what f of -1 is. Let me just see. And x equals f of a. So plugging in -1, we get what? Into our original function, we get -1 times 2 is -2, and then plus 3, so that's going to give me 1. So this is my f of a. In this case, it really doesn't matter though, right? Because if now I'm going back in here and plugging in 1 wherever I see an x, there's no x. So the way I could write that is df inverse dx. Remember, if we want to evaluate it, we could put this vertical bar, x equals 1 in this case. This is still equal to 1/2. Okay, so if I look at the derivative of my inverse function at x equals, in this case, f of a, I get 1/2. Notice if I put 1 over, so 1 over df dx at x equals -1, this is equal to 1 over 2, which is the same thing that we got here. And that's what we wanted to show. So that it was kind of tedious to do that when it would have been just easy just to find the derivative and go about it and evaluate that derivative of the inverse function. But it's not always so easy to find the inverse function, and knowing that how to find the derivative of our original function and using that fact and knowing that our X and our Y values, our input and output functions are opposite, we're going to look at it, our Y value, as if we plugged in the X value into our original function. Okay, so let f of x equal x cubed minus 3x squared minus 1. We're going to limit our domain, in this case, for x greater than or equal to 2. We want to find the derivative of the inverse function with respect to x at the point when x is 0. That is equal to f of 5. And so another way, I just pulled the derivative function for the inverse. And so if you want to find the derivative of the inverse function, which I forgot the prime here, evaluate it at b, this is equal to 1 over the derivative of our original function, not the inverse function, and then evaluating that at f inverse of b. So we need to remember this fact, right? If you have a point f of x, so f of x, this point is on f of x, and if we swapped it, f inverse of x, we swapped our y and x values. This is f of x, x. And so if this is, let's call it b, because I could use it b. So if this is b, f of b, then for our inverse function, my y value is my x value. My x value is my y value. So a couple things we have to do. We need to find the derivative of our original function. And that one's not too bad, right? So let's do that first. Let's find f prime of x. And so using the general power rule, bring our power down front, subtract 1 from our exponent. So x cubed is 3x squared minus the derivative of 3x squared. So 3 times 2, 6x, subtract 1 from my exponent. It's just 1. And derivative of a constant is always 0. So we found that derivative. The other thing that we have to do, though, is we have to figure out what is our y value when x in our case is 0. So when x equals 0, what is y? Actually, just stop for a second and think about this for a sec. Okay, so there's a reason why I was a little confused. I was pulling in 2 separate questions into one, and it wasn't this point here. And it was the point when x is -1. This is the same thing as f of 3. So let's look at that, f of 3. Oops. Actually, let's look at f of -1. If we go back in here, we plug in -1 wherever we see an x, right? We would have -1 quantity cubed minus 3 times -1 squared minus 1. And so this is giving me -1, and this is -3 minus 1, which is -5. That's telling me that's the same thing as f of 3. Three cubed minus 3 times 3 squared minus 1. Which is not the same thing. Right? Do you see that being the same thing? That little one piece in there of them saying this piece is confusing me.
Professor, earlier you wrote x equals 0 equals f of 5.
You know why? Because that was my mistake was that was problem 8 and I was writing down problem 7. So I was intertwining problem 8 and 7, the different pieces of the problem. So that was wrong
Oh,
in
okay.
there. So that's where I was thinking I was getting like caught up on how to do this because of that. I think what's confusing me is that they're saying x equals -1 is the same as f of 3, which is not true.
But Professor, the f of 3 is equal to -1.
F of 3 is negative. Oh yeah. F of 3 is -1. Okay, they're giving me the x value then for this. F of 3 is -1. Right, okay. They are going backwards. So they basically are saying, let's x equal 3. Okay, x equals 3. Then our y value is -1. And so we have a point at 3, -1. The thing is, when we go back in here and we use this, did I not bring it down? When I use this rule, notice I have to swap my x and my y values. And so I'm going to use in here -1, my y value. So when I was going through this, I kind of did it differently. So let's look at the following. So we know that the derivative, so f inverse of -1 is equal to 1 over the derivative, which we just found, of f inverse of this -1, which is going to be 3. Which is 1 over f prime of 3. So 3 times 3 squared minus 6 times 3, which is 27 minus 18, which gives us 9. Okay, let me pause, see if I did that right. Okay, so we did get it. Hopefully I didn't confuse you. Don't worry too much about this derivative of the inverse function for this test. So let's, this chapter was also going through, which I really liked, was taking derivatives of natural logs or logs, and then also using logarithmic differentiation to help us take something that was so complicated to be able to break it down into simpler log functions by taking the log of both sides, using implicit differentiation, and then taking the derivative. So let's maybe look at some of those examples.